Hello everyone, my name is Siqing, a third-year PhD student from Ohio University. Today I'm going to present our work of wireless interconnect-based deep neural network accelerator, abbreviated as WiNN. Here is the outline of this presentation. First, I will introduce the background of DNN and accelerators, the motivation why we exploit wireless interconnections for DNN accelerator design. Then I will elaborate our proposed accelerator architecture and the microarchitecture. To better understand how our proposed architecture accommodates the state-of-the-art DNN workloads, we will walk through a detailed example. Finally, we will conclude with simulation results. Deep neural networks are currently the foundation for many modern artificial intelligence applications. We have identified that the DNN is fast evolving in terms of size, depth, and complexity. As you can see in the red top figure, modern deep neural networks has increased to 1,000 layers compared to the first generation DNN model, AlexNet in 2012. Both academia and the industry has turned to specialized accelerators to address the highly parallel computation of DNNs. Unlike traditional computation workloads, DNN are both computation and memory intensive. Execution latency and energy consumption are critical, especially for edge devices. Therefore, dedicated ASICs are explored for DNN. Furthermore, researchers and architects of DNN accelerator switch to utilize emerging technology to address the limitation of conventional electrical hardware platform. For instance, wireless interconnection shows great potential in providing the parallelism, bandwidth, and energy efficiency, which is exclusively required for DNN. We demonstrate a typical wireline communication paradigm in the red figure. Messages have to propagate through multiple intermediate switches to get to the destination, incurring high latency and energy dissipation. The situation is getting worse when the accelerator design scales up. Wireless interconnections inherently support distance-independent one-hop communication, which alleviates this problem very well. Prior works have reviewed the potential of on-chip wireless interconnections to provide high communication bandwidth, no excess latencies, and high power efficiency, as I cited at the bottom. Here is the overall architecture of our proposed accelerator named WiNN. WiNN consists of global buffer, which connects the off-chip DRAM and the on-chip processing element array. We have two global wireless transceiver arrays. They are connected to the P array from the left and the top. Wireless transceiver arrays assign one transmitter and the antenna for each row and column of the P array, which constitutes a XY dimension order wireless network. We modulate the wireless channels of XY axis in different central frequencies to minimize the interference at the cross points. Each processing element consists of a local memory, computation unit, and a wireless receiver. Each processing element can receive the weight data and the inputs through the internal wireless receiver. The left figure shows the microarchitecture of the processing element. Two wireless receivers colored in red and green obtain weights and inputs through the external antenna respectively. The adder and the multiplier fetch data from the register files and perform a multiplication and accumulation per cycle. We use on-off key modulation for the transceiver as shown on the right. The modulation scheme uses an integrated modulator and power amplifier in the transmitter. By switching the power amplifier only when 1 is observed, the average power dissipated is reduced by 15%. Here I will introduce the proposed data flow and walkthrough example. Existing data flows are classified by how data is temporarily mapped on the hardware. For example, the weights being reduced inside the P over time is called weight stationary. They are not related with data distribution and movement. To best exploit the multicast capability of wireless channels, we propose a new data flow MW, multicast for wireless. Essentially, MW data flow deploys the X dimension wireless channels to multicast weights for each P in the row, and Y dimension wireless channels to multicast inputs for each P in the column. Here is a walkthrough example to show how MW data flow is implemented on WiNN. In MW data flow, as shown in the first row of the timing table in subfigure B, weights are spatially mapped to all P in a row for each time step. Therefore, The horizontal wireless channels can be used to implement this multicast traffic. Input activations are multicast by the vertical wireless channels to the corresponding column as shown in the second to the fourth row. Due to the one-hop multicast communication of wireless channels, the example convolution task only takes 16 cycles on WiNN, while traditional wired mesh takes 30 cycles, nearly 2 times more. We evaluated the proposed architecture on 3 representative DNN workloads, AlexNet, VG16, and ResNet50 on SAFA 10 dataset. We compiled the latency and energy consumption of WiNN to other mechanical log-based accelerators. These include traditional mesh, bus-based network, DNN-optimized microswitch, and hierarchical mesh as proposed in Iris v2. We further compile WiNN to a wireless interconnected DNN accelerator called WiLock. As shown in the figure, WiLock and WiNN achieve lower latency than any other mechanical counterparts due to the deployment of wireless interconnects. WiNN reduces the latency further on MW data flow compared to WiLock because WiLock only supports the broadcast of weights. Finally, we conducted a comprehensive comparison between different accelerators on AlexNet in this table. We normalized the hardware resources for file comparison. We re-implement Iris v2 and WiLock with 256 Ps and 500 MHz call frequency and 45 nanometers technology. When compared to Iris v2, WiNN achieves 1.7 times higher performance per watt and consumes 1.6 times less energy. When compared to WiLock, WiNN achieves 1.9 times higher performance per watt and consumes 1.1 times less energy, even with a half of the wireless bandwidth. When compared with WiNN, WiNN achieves 2.3 times less energy for AlexNet. To make a quick summary, the major contribution of our work is to propose a wireless interconnection-based DNN accelerator called WiNN. This architecture is featured by efficiently implementing broadcast and multicast by using wireless channels. We further propose a dedicated data flow that maximizes multicast data reuse opportunities to achieve low latency and energy efficiency. Our simulation results show that WiNN achieves solid performance improvements in terms of latency and energy consumption when compared to state-of-the-art magnetic link-based accelerators and wireless accelerators. Here is everything for the presentation. Thanks for listening.